Okay, let's go ahead and get started here. Just a quick review of what we've done so far. So uh, we've gone over some of the basic concepts in SolidWorks that you should know. Some key concepts there are how to extrude, extrude cut, smart dimension, how to build some basic simple profiles and 3D geometries. And then in the last class, we started with an introduction to COMSOL multiphysics, and I walked you guys through how to set up the basic workflow in COMSOL, and we did it for a scenario where we're modeling a load on a wrench. Okay, so we did the basic steps of COMSOL, and the basic workflow is to set up the physics, what kind of physics you're using, set up the study, whether it's going to be a steady state or transient state study. In our example in the last class, we did steady state. And then either build the geometry or import the geometry, and then to apply material properties, set boundary conditions, and then do the meshing, and then compute the study. Let's go ahead and pick up where we left off in the last class. I'll just quickly walk you through that again. Let me go ahead and close this and open a new one. I'll just quickly walk through the steps again. Again, I have my VPN connected. Okay, here's the VPN. Okay, so you got to be connected. So, and then I can go ahead and launch COMSOL. For you guys, you will have to remote desktop into a computer on campus and then launch COMSOL. Okay, so again, once COMSOL launches, we can use the model wizard to set up. I'll just quickly go through the steps from last class. The type of physics we're using is going to be solid mechanics. We're just going to continue talking about a little bit more about that example with putting a load on a wrench. So once I add the physics, I then click on study, and in this case we're starting with stationary study or steady state, meaning the loads don't change over time. And I'll go ahead and press done, and it'll set up the workspace for me, the graphical user interface for me. And I'll go ahead and bring in the geometry we're working with. So I'll right click on geometry, click import, and I'll browse to the wrench geometry. Remember, COMSOL file extension is this mph bin file. So I'll click on that, press open, then click on import, and I have my geometry that I want to work with here. Okay, and again, we're going to be modeling putting a load on the end of the wrench, and making this part of the bolt fixed, as if it was fixed to the wall or something. And the things we want to learn, or the type of questions we want to ask, is at what point will this at what point is the maximum stress is occurring, and at what point is perhaps how much is this bending, and where might it break. Okay, so that's what we hope to learn from this model. And again, we need to tell the computer what kind of material this is. So I'll just right click on materials and click add material, and I'm going to use the built-in library here from COMSOL, and I'm going to apply structural steel to both the wrench and the bolt. Remember, there's two domains here, domain 1 and domain 2. And again, it's going to give us all the material properties of the structural steel. I want to take a second real quick to review some of these material properties. As density, you should know what density is. But let's talk a little bit more about Young's modulus and Poisson's ratio. So, yeah, before we get to Young's modulus, let's just briefly review what is stress. Okay, so stress is denoted by this sigma, and it's force over area. Okay, and the units for stress are newtons per meter squared or pascals. Okay, so you can think of stress as a load. Okay, you know, I asked my wife one time, what is stress, and she said it's 2 kids and a dog. And I laughed a little bit, and I thought, yeah, in engineering we don't really think of stress that way. But then I was thinking, oh, I guess it kind of relates. If I'm under a lot of stress, it feels heavy. I'm under a load. I was thinking, oh, okay, it's force per area. So this is what stress is. This is why we call it stress. It's like pressure, okay? It's force. It's a force per area. And the units are typically given in pascals. So, so that's what stress is. Think of it as a load on top of something, okay? So let's talk about strain. What is strain? So this first one here is stress, which is denoted as sigma. Now, strain. Let's talk about strain. Okay, and you could think of strain as deformation. Okay, so for example, if I have a cube, okay, and I put some stress on it or load on it, okay, and its original length, let's just call it L, or height, let's just call it L. Well, if I put a load on it, this may shrink, right? Or it may deform under the load, okay? So L might become shorter here, okay? Maybe I'll call that the first one maybe will be L prime, and then this one be L double prime, okay? In short, this distance here is delta L, okay? So what is strain? Strain is you can think of strain as the percent change in deformation, okay? So you can think of it as percent change in deformation, or change in length. So it's going to be delta L over the original length L prime. Maybe prime, yeah, prime was the original length. Okay, so you can think of it as the key word here, deformation. Okay, how much it's deforming. And what are the units here for strain? Well, the units for delta L, if the units are given in meters, okay, the units are meters. And if the original length is given in meters, it's meters. So it's meters over meters. It cancels out. It becomes unitless. Okay. So it's really a percent change in deformation. Okay. So that's stress, this is strain, and as it turns out, stress and strain are related to each other. So, and you can see the relationship if you draw something called the stress-strain curve, okay? So if you put stress, sigma, versus strain, okay, and plot their relationship, the relationship might look something like this. As you put a load on something, okay, if you put a certain amount of stress on something, you might expect that it will deform a little bit, okay, and the relationship might look something like this, okay. And how do we read this? Well, as stress increases, okay, strain increases. So you might think of a bridge. If you put a load on a bridge, the bridge may deform, and the more load you put on the bridge, the more stress you put on the bridge, the more it's going to deform, or it'll have more strain, okay. And this relationship between stress and strain is related to each other by something we call Young's modulus, which is the slope, okay. So the slope, which is, you know, rise over run, okay, so how much it rises for how much it runs, okay. The slope is what we call Young's modulus of elasticity, or Young's modulus. Okay, and we usually denote Young's modulus as big E, okay. So Young's modulus is the stress relationship between the stress over the strain, okay. Okay, or you can think of it as the slope, rise over run, okay. So that's what Young's modulus is. And so, again, stress and strain are related to each other, and it should make sense. The more load or the more stress you put on something, the more you would expect it to bend or deform a little bit, okay? And so this relationship is shown in this stress-strain curve. So this is called the stress-strain curve, okay? Which shows the relationship between stress and strain. And again, the slope is Young's modulus. So you would think of something that has a high Young's modulus, something like, let's say, for example, something with a high slope, okay, like this, would be something like steel, okay. it would have a high Young's modulus. Why? Because you can put a lot of stress on steel and it won't deform very much. Okay, something with a low Young's modulus. Okay, maybe something like rubber. Okay, even adding a little bit of stress to the rubber deforms it a lot. This might be like rubber with a low Young's modulus. Okay, meaning that even with a little bit more stress, it deforms quite a bit. Okay, so these are, again, as we are modeling these things, it's important that you have an understanding of the governing equations, the basic physics. Otherwise, you could make many mistakes. So if there's a unit, or if there's a constant, or something that you don't understand, you should stop and review it. Okay, so when modeling structural mechanics, these are some of the basics: stress and strain, Young's modulus. Another one of the basics is called Poisson's ratio. So let's review Poisson's ratio. But before we review Poisson's ratio, let me show you guys the stress-strain curve a little bit more here. Okay, so again, the stress-strain curve shows the relationship between stress, which is the load, okay, versus the strain, which is the deformation. Okay, and again, the slope here, the slope is Young's modulus. Okay, and so in any material, as you increase the stress, you'll get so much deformation. Okay, as you increase the stress, you'll get this much deformation. Okay, and it's important to note that at some point you'll reach something called the yield strength. Okay, that means you've and notice how it'll change the curve here, because it's because you've reached the yield strength, you actually get some buckling here. Okay, or the material is actually failing at this point. Okay, and because it kind of cracked or broke, you'll see deformation occurring in strain. Okay, remember, strain is like deformation. Okay, you see this much deformation occur, but no increase in the stress. That's because it's reached its yield strength. Okay, so that's an important part there. And then typically, once things break a little bit, then they kind of recover, and you can add a little more stress to them, and they'll just continue deforming a little bit until they reach their ultimate strength, meaning it start failing and continue to fail all the way to fracture. Okay. Another important word is this word necking, and let's just review real quick what is necking. So if I have a piece of material like this, and I pull it on both sides, okay, that's going to be applying, again, a stress to both sides, or a load. What will happen to this material is, as it undergoes this points on this stress-strain curve, and starts to, let's say, starts to become stretched. So I'll just draw it here, stretched Okay, so it's getting stretched in both directions. What will happen is in this lateral direction, it'll actually start getting thinner. This is what the necking is. And in fact, the necking will start to like bow and look like something like this. Okay, let me try to draw that again. 1 second. And undo that. Okay. So you start getting some necking, meaning you're getting a narrow neck in the middle. This is also called dog boning, okay? Where the material starts getting thinner in the middle as you're pulling on both ends. So that's called necking, all right? Also called dog boning, because it kind of ends up making it look like a dog bone, okay? So this is the relationship between stress and strain. Again, some basic concepts, basic things that you should understand. If you're going to be modeling structural mechanics, you should know what is the yield strength, what is Young's modulus. You should know what is necking, what is stress, what is strain, how are they related, okay? So these are, this is how they're related. And like I was also saying, another important concept is something called Poisson's ratio. So let's go back and let's take a look at Poisson's ratio and what is Poisson's ratio. So Poisson's ratio is another important principle that you should understand if you're going to be modeling structural mechanics. And basically what it is, if you can imagine, if I have an object, okay, and I put a load on top of this object, okay, so let's say we put a load on this object. Well, this object is going to get squished, right? But as it gets squished, it also gets wider, okay, like this. Okay, so notice we had the original length L, right? We have delta L here, and we have the new length here, but also in the lateral axis, okay, or perpendicular to the stress being applied, notice the object got bigger in this direction, okay? So you can kind of think of it as if it got squished. If you push on something from the top, it's going to come out on the sides, okay? Now, so that relationship between longitudinal strain and lateral strain is what we call Poisson's ratio. So again, Poisson's ratio is denoted as this nu, and again, it's a negative strain in the y-axis. Let's call this the y-axis and this the x-axis, which we'll call the longitudinal strain. It's the ratio of the longitudinal strain to the axial strain, which remember, strain is really nothing but deformation, okay? So the strain in this axial or x direction is epsilon x, and the strain in the y direction is epsilon y. So it shows it's basically a ratio of how much this material is getting squished, right? When you put if you can imagine putting a load on top of this box and the box getting squished, well, it's going to come out the sides, and so Poisson's ratio covers this this material property. All right, let's talk about two other important things that you need to know. You should also know what is creep and what is the von Mises stresses. Okay, so let's first take a look at what is creep. Okay, so again, the stress, when looking at the stress strain curve, okay, you see the relationship between stress and strain is that when stress increases, so does strain. Meaning when you increase the load on something, the more deformation you get. There is also another scenario where you have a constant load, and yet you get deformation. So if you imagine the stress is constant, and yet we're still getting strain or deformation. Okay, now this can happen, this is called creep. Okay, and I'll try to give you a visual of that. Okay, so a good example of creep might be if you can imagine a bridge. Okay, imagine having a bridge, okay, that's sitting on top of two pillars, okay, and let's say you put a load on top of it, okay, a load of cargo on top of it, okay, so this load is sitting on the bridge. Well, what's going to happen to the bridge? Of course, the bridge will start to sag a little bit, right? Now, what if the load is constant? Meaning not increasing the load, not putting anything new on the bridge, but over time, the bridge starts to deform more. Okay, now why is it deforming more when the load isn't being increased? This is called creep. Okay, this is where the bridge is getting tired. Okay, and so you can imagine if I ask you to hold your hands out in front of you, and I put in your hands two heavy school books, and just ask you to stand there. What will happen after 10 minutes? Well, your hands will start to drop. Why? Because you're getting tired. You're starting to experience fatigue. Okay? Well, in structural mechanics, this is called creep, where the load doesn't increase, meaning I didn't add any more books to your hands, but yet your hands are going down over time, is because you're experiencing fatigue. So it has a constant load, and yet you're still experiencing some deformation. So with this bridge, if we have a constant load on it, given enough time, it'll continue to sag because of creep. Okay, so this is another material concept that you should understand. Okay, so another important concept that you should have an understanding of is these von Mises stresses. Okay, so let's review real quick what is a von Mises stress. I'll just do a quick search online for von Mises stress, and I'll just go to this first link here. Okay, and let's take a look at the von Mises stress. Well, in short, the von Mises stress take into account the complex multi-directional or multi-axial stresses occurring on an object. So, for example, if I have a bridge, let's go back to our bridge example. If I have this bridge and I'm applying a load to the bridge, and let's just say this is the x-axis, this is the y-axis, and I want to try to determine at what point will this bridge break, okay, with this load, or how long will it take for this bridge to break, okay. And let's say if I only consider the stress in the y-axis, okay, and the deformation in the y-axis, I would be wrong. Why? Because this bridge is a more complex three-dimensional structure. Okay, it has more than just an x-y axis. It has a z-axis, and as you put a load on this bridge and it starts to undergo deformation or strain, that's causing other loads and other strains in the other axes, in the x-axis and in the y-axis. In fact, it's starting to cause moments on both sides of the bridge. You're starting to get torsion or maybe even some twisting. And so if you only take into account the load in one axis, you will be doing it wrong. And in fact, the bridge may fail in another axis before it fails in the y-axis. Okay, it may fail in the in a different axis. So the von Mises stresses, okay, take into account all the different loads in the different axes and the different kind of loads that can take place. So this sigma 1, 1, that's the stress in direction 1 on face 1, which might be like y going in the y direction and on the y face. 2, 2 would be on like the x face and going in the x direction. Okay, so these are normal, these are the normal loads. Okay, and here we take into account the stress going in the x direction being applied to the y face. Okay, so these are the shear stresses here. Okay, so this von Mises stress equation takes into account the multi-axial loading conditions and the complex stress that's occurring, and can be used as a more accurate measure of where this material will actually fail. So this is called the von Mises stress. You can remember it as kind of multi-dimensional or multi-axial stresses, all the stresses in all the directions being taken into account. Okay, so let's go back to our wrench problem, okay? So again, we just added material properties to this wrench. That includes the density of the material. It includes Young's modulus, which we just covered. It includes Poisson's ratio, which again, we just covered as well. So now the computer knows what this material is. It's structural steel. The next step was for us to apply our boundary conditions. So I right-click on solid mechanics and click on fix constraint, and we're going to fix this part of the wrench to the wall, okay? And then I'll add a boundary load, okay? And put the load on this end of the wrench as if I'm putting my hand on it. And we're going to put total force in the negative z-axis of 150 newtons, okay? Then I'll go ahead and build my mesh, and I'm going to make a slightly finer mesh to avoid any errors or any warnings, okay? And then I'll go ahead and compute my study, okay? So this is as far as we got in the last class, and notice down here you can see the green progress bar is computing, okay? So the computer didn't crash, it's actually working, okay? Okay, so this is where we left off in the last class, where we could see the results in this default plot where it plots the surface von Mises stresses, okay? And so again, the von Mises stresses are taking into account all the different stresses in the multi-dimensional, multi-axial directions and finding where the greatest stresses are occurring. So this is again where we ended up where in the last class where blue is the lower stresses and red are the higher von Mises stresses. So important to note, let me show you a couple of other ways on how to get data out of this, out of these results, okay? So again, you need to ask yourself, what am I trying to learn? What is this model going to teach me? What questions are we trying to answer? So let's just say we wanted to know how much, where is the maximum stress occurring? Okay, so we could do that. In fact, if we click on any part of the surface here, notice it'll plot in this table down below the x, y, z coordinates of that and the value. Okay, so if I click on the red here, it'll be higher stresses. Okay, 3.25, and this is going to be times 10 to the 8. Okay, if I click on the blue, it'll be lower values. This one's going to be times 10 to the 7. So you can click on different parts and get the value. But how do we find out? Let me show you how to find out, well, where's the maximum one occurring? Well, we can do that over here in our results. Okay, notice the default plot is to plot the von Mises stresses. Okay, and that's what we call a surface plot. And that's what this one is here. Notice it's plotting the von Mises stresses. And look, the units, notice the units are in stress, which is newtons per meter squared. This is what's being plotted. And overlaid on top of it is a deformation plot. Okay, so we have a deformation plot also being overlaid, and so you can see how it's being deformed. And it's being deformed at a scale of the scale factor here. Okay, so let's just take a look. Let me show you how to add more information to this. If I right click on this surface plot, okay, sorry, excuse me, right click on the stress plot and go to more plots. Look at, I can have different options. I can click on this maximum and minimum surface, okay, so it can add where the max is occurring and where the minimum is, and the default is to show how much show the displacement. Let's take a look at that first. Let's just take a look at where's the maximum displacement occurring. That's what this expression is. Notice the units are in meters, and if I click plot, it'll add it'll add the max over here, showing me that the maximum displacement is occurring right here, and how much. I can change the units too. Let's go to millimeters, and I'll plot that. So this is displacing, the maximum displacement here is 1.83 millimeters. The minimum displacement is, as anticipated, this area, this point where we had fixed, we're fixed to the wall, so it's 0, it's not moving. Okay, so that's one way we can look at get some more information out of this. How much is this bending? Well, it's bending 1.8 millimeters. Okay, so we can do the similar thing to plot the maximum von Mises stresses. So again, if I right click on the solid plot here, go to more plots, and add another max min surface. Okay, and this time I'm going to change the expression from solid displacement to the von Mises. And how do I do that? I click on this icon here to replace the expression. Okay, and I can do a search in here for von Mises stresses. And so under the stress, I see that the option there for von Mises stress. Double click it, and notice it replaces this with the solid dot Mises variable. That's the von Mises stress. Also notice the units were updated, and the units are as expected in newtons per meter squared. So I'll go ahead and click on plot, and notice it plotted the maximum stress is occurring right here. Okay, so here is where the maximum stress is occurring. Okay, so it looks like if anything's going to break in this system, it'll probably be the bolt head, and the minimum stress is occurring over here. Okay, so this how you could get some data out of these results. Okay,